wouldn't be able to make the jump and they'd stay where they are. Conversely, hit by light rays that are too energetic, they could jump over several such zones and even be expelled from the atom they belong to. This was figured out by mankind at the beginning of the 20th century. It may not seem to be groundbreaking, but it is. Einstein received the 1921 Nobel Prize in Physics for figuring this out as regards the atoms that make up various metals. 14. Decades of experiments done ever since on all the known atoms in the universe then made scientists realize that the energy needed for any electron to move from one orbital to another within any kind of atom is specific to the atom it belongs to. And this is very, very fortunate for us, because different energies correspond to different light sources, and with our telescopes, we can of course collect light from pretty much anywhere. This simple fact means that scientists can tell what faraway objects like stars or gas clouds, or even distant planets' atmospheres, are made of, without ever going there. Here is how. Imagine a perfect source of light, one that shines all possible wavelengths of light, from the least energetic to the most, in all directions. Such a perfect source creates a glowing sphere of brightness. If there is an atom standing some distance away, its electrons, blinded by all the incoming light, may, in a frenzy, swallow all the ones they need to jump from where they are to a more energetic orbital. When they do so, they get excited. Excited? Yes. Excited. That is the proper technical term for what happens. They are a bit like children being offered sweets at a party. And just as it is not hard to work out which sweets the children preferred afterwards, you can figure out which types of light an atom gobbled up by checking which ones are missing in its shadow. All the unused light passes through the atom unhindered, and you can detect their signature wavelengths quite easily. The ones that are missing, on the other hand, appear as small dark patches on an otherwise continuous rainbow of colors and light. Such a chart is called a spectrum. 15, and the dark patches are called absorption lines. Scientists can tell, just by looking at the light wavelengths that are missing from a spectrum, which atoms are standing in the way of a light source. Using light, you thus have a way to figure out what type of matter is out there, without going there. And all the light-gathering telescopes mankind has used so far tell us that all the stars in the universe are made of the same stuff as the sun, and as the earth, and as ourselves. All the cosmic objects of the night sky are made out of the same atoms as we are. If it were not the case, our telescopes would tell us so. The laws governing nature can thus be presumed to be the same everywhere. This is why the first cosmological principle is considered correct by everyone. What a relief! In fact, it is such a good piece of news that being in outer space, you decide to immediately have another look at faraway galaxies, to figure out for yourself what they are made of. Aren't they pretty, with their beautiful spectra full of lines corresponding to hydrogen, helium, and... Now wait. Hold on. Something is wrong. Looking at the spectra you gathered, you realize that the missing lines in the light coming from faraway stars are there all right, but they are not where they should be. Whereas the electrons of some chemical elements here on Earth are excited by blue light, the same electrons within the same chemical elements out there, in faraway galaxies, seem to relish slightly greener hues to jump from one orbital to another. And atoms that are yellow-hungry here on Earth seem to prefer orangish light everywhere else. And orange-craving ones here like it red out there. Why? How can that be? Are all the colors shifted in outer space? Or did we make a mistake? You look again at different faraway sources. But there is no doubt. All the colors are shifted towards the color red. And it gets even worse, the further away the source of light, the more pronounced the shift. Damn. It was all too easy. So what is going on? Are the laws of nature different in different areas of the universe after all? If you could stroll the land of a planet similar to Earth, a planet orbiting a sun-like star billions of light years away, would its sky and oceans and sapphires be green, would the plants and emeralds be yellow and its lemons red? Well, no. If you traveled there, you'd see the alien world as we see it here, a world in which lemons are yellow and skies blue. The reason for the observed color shift is not that the laws of nature are different far away from us. It goes deeper than that. It even changed everything mankind had believed for more than 2,000 years. Have you ever tuned a guitar, or any other stringed instrument? Did you notice that the note emitted by a plucked string changes when one adjusts its tuning pegs? The more one stretches the string, the higher the pitch, right? Well, what you just saw in the sky corresponds to the same phenomenon, except that sound is replaced by light, and the string is not a string. In space, light does not travel, or propagate, on a string, but through the fabric of our universe itself. And to explain the color shift you just detected, this fabric has to be involved. Why? Because for this shift to affect all the possible colors in the exact same way, it cannot be the case that light itself is to blame, but rather what it travels through. Pluck a string and tighten it with the tuning knob, the sound it emits is shifted towards a higher pitch, not because something happened to the sound, but because the string got stretched. And a guitar string is stretched in the exact same way for all the notes. Now imagine you could stretch the fabric of our universe, like you would stretch a guitar string. Stretch it once and all the wavelengths of all light propagating on it would immediately become higher pitched. Why? Because light can be thought of as a wave and the stretching would increase the distance between two consecutive crests, the wavelength. Blue would become green. Green would become yellow, yellow red, and so on. On a spectrum, it means that the actual colors of the universe get shifted towards the color red. They are redshifted. Now instead of stretching the fabric of our universe once, imagine it somehow has been continuously and steadily stretched. The further any light has been traveling, the greater the redshift it will have been subjected to before reaching Earth. With such a scenario starting far away, a blue ray will steadily become green, and then yellow and then red and then invisible to our eyes, infrared and then microwave. Knowing how much the colors emitted by a faraway star differ from their initial colors once they reach Earth would then enable you to tell how far away that star is. But is this true? Is that how the fabric of the universe behaves? It is. That is exactly what you saw in the sky. But what does that mean in practice? It means that the actual distance between faraway galaxies and us is growing all the time. It means that space stretches, and therefore grows, on its own, in between the galaxies. It means that our universe changes with time. Countless experiments have now confirmed this, and scientists have learned to accept that idea. We do live in a changing, growing universe. Einstein didn't like it though. Nobody liked the idea, a century ago. For our ancestors, be they scientists or not, the universe had always been the same. But they were wrong about that. To be clear, it is not the galaxies that are moving away. It is the distance that separates us from the already faraway galaxies that is growing. It is the very emptiness of space that is being stretched. Scientists have given that phenomenon a name. They call it the expansion of the universe. And contrary to what one might think, this does not mean the universe is expanding into something. It means it expands and grows from within. Now, before drawing any hasty conclusions and wondering what could have caused such an expansion, you may want to check all this by yourself. So imagine you are rich as can be and that you have 100 friends. Being curious about our universe, you give each of them $1 billion to buy a powerful modern telescope and travel all around the Earth to gather the light from as many faraway galaxies as they can. A few months later, you invite them all to your mansion to present their finds. About half of them were real friends and show up, the other half having preferred to keep the money. But it doesn't matter, for all their stories are identical. Wherever they went, whether in China, in Australia, in Europe, in the middle of the Pacific or in Antarctica, all those who came back to you saw the same phenomenon in the sky, right above their heads. Faraway galaxies had a strange color shift. They were all receding into the distance. And the further away these galaxies were, the faster they were fleeing away. They all witnessed the expansion of the universe. What should we make of this? As you think about it, a very strange idea should continue to grow in your mind. First there was this strange visible universe that was a sphere centered on you, and now this. Could it be true? If everything, everywhere, moves away from the Earth, does it mean that all the mothers on Earth are right in thinking that their child is at the center of the universe? As amazing as it sounds, it does seem so. What a lovely piece of news, what a joyous day. If some of your friends are around as you read this, you can uncork some champagne. We are special, after all. Especially you. At last. Vindicated. Copernicus was wrong. He should have listened to his mother. Mothers are always right. But wait. How about mothers on faraway planets in other galaxies? Were they to exist and think like our mothers, would they be wrong about their children? Or is that a proof that there aren't any mothers anywhere else? Surely not. Despite what you have seen, just as Copernicus told us 400 years ago that we are not at the center of the solar system, most scientists today take it that our position in the universe is no more significant than any other. Strangely enough, this doesn't mean we're not at the center of our visible universe. We are. But every other place also is. Every place is at the center of the universe that is visible from there. This very strong belief even led scientists to the following additional cosmological principles. 16 To guess what happens out there, very, very far away from our planet, scientists assume that there is no preferred position anywhere whatsoever. That is the second cosmological principle, and that if one selected observer was to travel around, all directions would always look the same for him or her, with faraway galaxies always moving away from where he or she is, just like they are moving away from us here on Earth. That is the third cosmological principle. If you now take a moment to think about it before your friends give up on the champagne, cosmological rule number 3 sounds trivially wrong. The world obviously doesn't look the same as seen from where you are now, reading this book, as from under your shower. So a clarification is in order. The third cosmological principle does not bother about what is near you. It is concerned only with the big picture. With scales much, much bigger than galaxies. It says that the universe, on extremely large scales, looks similar whatever direction you look in. Still, this sounds wrong, doesn't it? Didn't you travel throughout the universe in part 1? Didn't you see places far away that did not look like the universe as seen from the Earth? You even crossed a patch of space thousands of light years thick where no star shone, the so-called cosmic dark ages. How can the universe look the same from the Earth and from a place where there are no stars at all? Well, it is now time for you to realize what I truly mean when I say that you did not travel, in part 1, through the universe as it is, but through the universe as it is seen from Earth. It is not quite the same thing. Remember, the universe that appears at night does not correspond to what our universe is now. It corresponds to a slice of its past history, a history centered on Earth because we are on Earth. We receive picture postcards every day, from everywhere. According to cosmic rule number 3, aliens living on a faraway world should see a universe exactly similar to ours. Not in detail, of course, but on large scales. They, too, would be surrounded by the sum of all the information that reaches them from their past. They too would see in their night sky a slice of the history of our common universe. They'd have their own cosmic dark ages and surface of last scattering. They'd have it all, even if their slice did not intersect our own. In the end, to understand our universe, to get the whole picture, all the past histories of all the points of the universe have to be added. Close-by places have histories that overlap a great deal. Of course, but places separated by great spatial distances may not have any of their pasts overlap at all. Still, they should all be considered equivalent. That is what cosmic rule number 3 means in practice. You will hear more about this later. Incidentally, this also means that even though you do not occupy a special position in this universe of yours, you still are, as your mother certainly thought, at the center of your visible universe. And if you feel like you had always known so, please let the joy flow through your body and mind. It is great news. I say it again, you are at the center of your universe. Now, what may feel less good is that so is your neighbor, he or she is at the center of his or her visible universe. And everyone else too. And everything else as well. We all are, everything is, at the center of our own universe, the universe we can probe with the light that reaches us. Only on some rather special occasions can two people's visible universes perfectly match. I will leave it to you to figure out when, and how, that can happen. So, that being said, it is time to look a little closer at this expansion that stretches the universe. Is that really what is happening? It is. The distances between faraway galaxies do stretch all the time. It doesn't apply to close-by objects, though, because gravity is locally stronger. Galaxies create a gravitational attraction that cancels out such expansion, both within their boundaries and around. Over large distances, however, expansion rules. The discovery of the expansion of the universe was made by U.S. astronomer Edwin Hubble in 1929, and the law that links the way the galaxies recede to their distance away from us is called Hubble's law. On the strength of this finding, Hubble can rightly be considered one of the fathers of modern observational cosmology. He is also the person who, with Ernst Opik, proved that the Milky Way is not the entire universe, that other galaxies exist beyond it. Two discoveries that would certainly be worth a Nobel Prize, were they to be made today. At the time, however, looking at the stars and trying to make sense of them was not considered part of physics, either by the physics community or by the Nobel Committee. As a consequence, Hubble never got a Nobel. But the rule changed after his death, and many a Nobel Prize has since been awarded to observational cosmologists. You shall meet some of them in this book. Now, as you are about to understand an extraordinary consequence of Hubble's expansion law, you will most probably be shocked by how bright scientists can sometimes be. With a lot of thinking and about twice as much coffee, they figured out that if everything that is far away in our universe is moving away from us now, then everything that is now far away must have been closer in the past. Wow. Talk about breakthroughs. You may try and do that reasoning again on your own someday. It is quite satisfying. Actually, although it may not seem to be much, it was a real revelation. As I said above, Einstein himself refused to believe it. Why? Why does it matter if faraway galaxies are moving away or, for that matter, were closer in the past? Remember, Hubble's observation-based law says that it is the distance between the galaxies itself that is expanding, not just that the galaxies are moving away from one another. In other words, it is the fabric of the universe that is expanding. Following this idea through, it must be the case that the universe in its entirety was smaller in the past. But how could that be? And can one prove it? One can. By looking far away again. The past lies there for us to receive its messages. And the wall you saw at the end of the visible universe confirms all this brilliantly, and you will see why in the chapter after next. First, however, you will have to travel to outer space again, to get a bit more acquainted with gravity. 6. Feeling gravity. Of the four fundamental forces that govern our universe, gravity is perhaps the one we are most aware of. 17 Every time you fall, every time you use the muscles in your legs to push yourself up to standing, every time you lift anything, your body is reminded of gravity's existence. Everything is affected by gravity. But everything also creates gravity. Including you, including those crystal vases your great-aunt in Sydney keeps giving you at Christmas. Talking of which, imagine you had one of her vases with you on your island. Look at it. Now drop it above a hard surface. It falls and shatters to pieces. You can imagine letting all your collection fall onto a hard surface, from as many different places on Earth as you can think of. Amazingly, they would always fall. And break. Wherever you are. Good. Not only will such an experiment rid you of your vases, it'll also prove a point: as long as it is denser than air, any object dropped on Earth will fall, just as Newton has thought since forever. What about an object lighter 18 than air, then? Why do helium balloons rise in the sky rather than fall? Do they not feel Earth's gravity? They do. But there is competition. Whenever objects are dragged down by the Earth, the densest tends to settle furthest down. If objects lighter than air seem to fly up, it is because the air from above is denser and takes their place. Were the air to be visible, you'd see it. But visible it is not, and you just see the result: objects lighter than air are pushed upwards by the invisible air that stacks up under them. Gravity is always attractive. It always makes things fall. But competition creates layers, and some objects have to move up to make room for denser ones. With this in mind, you can think of the Earth as a huge ball with loads of stuff sticking to its surface because of the steep curve it creates around itself within the fabric of our universe. All the objects you've ever seen slide down that slope, you slide down that slope, until a floor or something else denser prevents them and you and everyone from sliding down anymore. Rocks in the Earth's crust are denser than water. That's why the ocean lies on top of the hard rock beneath. Rocks and water are denser than air. That's why the atmosphere lies on top of our planet's surface, be it rocky or liquid. We humans live underneath about 100 kilometers of air sticking to our planet's surface. We are denser than the air. We don't fly. But we are lighter than the ground. So we stay on top of it. Sometimes, some objects or animals do manage to move away from the ground, up in the sky, but for them to do so requires energy, and it usually doesn't take long before they fall back. Unless, of course, they are lighter than air, which is unheard of for any animal. Now, how would everything fall into place if there was no Earth? It is Sunday morning on your tropical island. Your friends have been bringing you breakfast every morning since your strange mind trip, and they have clearly been more and more curious about your story. Some of them are even wondering whether you really did see what you keep saying you saw. Others have been struggling to get to sleep at night, worrying about the death of the sun. Rather unfortunately, these ones have been actively looking for ways to stop you talking about it all the time. And it seems they did find one. You open your eyes. Motes of dust flicker and dance in the morning sun rays, even though they, too, feel gravity, you think, as someone knocks on your door. Come in, you say, sitting up on your bed, expecting a smiling friend and perhaps a tray of fruit and coffee. The door opens. And there she is. Your great-aunt. From Sydney. Next to her are 3 bags, all filled with crystal vases. You did not think it possible, but they are even uglier than the ones you wanted to smash for your gravity experiment. She comes in, not in the least bit fazed to find you in bed, stands next to you, pats you on the cheek and hands you one of the vases, silently smiling, with a look of understanding on her face, knowing that words could not faithfully convey your joy at her surprise visit. With the vase in your hands, you close your eyes to keep calm, suddenly desperately wishing you were somewhere else. And as you open your eyes again, you are. Somewhere very else. In outer space. The villa, the sun rays, your bed, your great-aunt, all are gone. You are back among the stars, as in part 1, but everything seems much safer than back then. You can't help but break out into a big smile as you look around. No sign of an immediate explosion. No molten earth. All the stars are far away, all is quiet. You are floating in the middle of a seemingly infinite darkness studded with tiny lights. When, in the first part of this book, you found yourself in space, you were just a mind. Apart from the moment you got ejected by a black hole, you did not feel anything at all. This time, however, you are about to experience something different. You are still on a mind trip of sorts, but you did not leave your body behind. It is here, wrapped within the protective shelter of a spacesuit's fabric, experiencing weightlessness. It all seems so real that you actually feel rather sick, but you soon get over it, and it eventually occurs to you that although your great-aunt is no longer around, you're still holding the vase she just gave you. You look around again with a grin, but there's nothing at all to smash it against. No earth. No star. Putting on a brave face anyway, you decide to do yet another gravity experiment. You open your hand, at arm's length, and let the vase go. As far as you can tell, the vase stays right where it is. A minute passes. And then another. And then, suddenly, after another minute goes by, another minute has passed with still nothing happening. Or maybe the vase moved a bit towards you. But not by much. Nothing worth reporting. Eventually, tired of staring at this monstrosity of a vase, you push it with the tip of your finger and watch it as it slowly moves away in what appears to be a straight line. Good riddance. Had you not pushed it, the vase would have stayed right next to you. It wouldn't have fallen. What could it have fallen towards anyway? With no planet or star around, there's no notion of up and down, or right or left. In the middle of nothing, all directions are equivalent. There's no ground of any sort for the vase to head to unless, of course, you consider yourself to be the ground. But that would be to insult yourself, wouldn't it? Well, you shouldn't take anything too personally when nature is involved, for after a long while spent doing nothing, to your great dismay, you do see the vase coming back towards you. Gravity is at work. The gravity you create. A strange question pops into your mind, though. Is it the vase that is moving towards you or you towards it? For all you can tell, it may as well be the vase that is the ground and you who are falling towards it. Unfortunately, you do not have the time to dig that idea through because an asteroid shoots past right next to you, snatching you and the now rather close-by vase with its invisible gravitational fingers. Had you been asked, you'd probably have said that, being heavier, you'd be first to hit the asteroid's ground. But no. That is not what happens. You and your vase reach that rock's dusty surface simultaneously and, as your feet hit the soft ground, you immediately grab that failed piece of art to smash it against the asteroid's surface. Unfortunately, the asteroid's ground isn't as solid as Earth's, and the vase doesn't break. Instead, a vast cloud of cosmic dust now surrounds you. Annoyed, you pick the vase up and throw it spaceward, with all your strength, to get rid of it once and for all. This time, there's no way it'll come back, you think, and you do feel relieved as it disappears into the distance, through the dust cloud, doomed to spin on itself forever. Alone at last! You can now relax, enjoy the unspoiled view, and figure out how to experience gravity more deeply than anyone has before. As you wonder about this, it occurs to you that the rock you happen to be standing on is not moving straight any longer. Its trajectory just bent to head towards a dark and frozen world, a planet without a star, which wanders in the middle of nowhere on a probably vain quest to find a shining new home. There was danger around, after all. You just hadn't spotted it. For a moment, as your rock accelerates down towards the planet, as you feel your guts lurch up inside you, you are almost certain that you are on a perfect collision course, on your way to smash into the cold and very dead world's surface. You've heard that when facing imminent death, people usually have long-lost memories return, or see their life unfold before them. No such thing happens to you though. You can't think of anything but your great Tan's face as you blame her and her vase for the certain death that awaits this body of yours. In a heroic effort to save your life, you push down hard and jump from the asteroid and start swimming away from the planet. Right after doing so, you realize two things. Contrary to what you thought, you are not on a collision course, and secondly, although jumping from an asteroid is certainly possible, it is impossible to swim in space. As if on an interstellar roller coaster ride, you accelerate more and more as you slide down the slope the planet creates in the fabric of the universe. As expected, you end up missing its surface by a few thousand miles and swing around its dark, cold ground only to find yourself rapidly hurled spaceward again with your asteroid, like a slingshot, at a much greater speed than before the fall. You and your asteroid effectively just stole some energy off that world, some kinetic energy, like a golf ball on a mini-golf course that, missing a cunningly moving hole, spins round its edge before being ejected and rolling faster and discouragingly further away than where you hit it from. A still hole cannot do that, nor can a fixed world. But a moving hole can, and so can a moving planet. A few minutes later, as the dead planet disappears into the distance, you land back on the surface of your asteroid. Strangely, you realize, it had never stopped attracting you, and, stranger still, you notice that you both followed a very similar path around the now-gone lost world. That a vase weighing a 40th of your weight should fall like you towards an asteroid may be surprising, but that an asteroid, a rock the size of a small mountain, should fall like you towards a planet is vexing. Still, that is what happened. Objects, it seems, all fall in the exact same way towards planets, or towards each other, regardless of their mass. As curious as it may sound, even the sun and a feather would fall in the exact same manner towards an asteroid, or a planet, or anything. It is so, because being subject to gravity means journeying down the slopes that matter and energy creates in the fabric of our universe. Understandably, you sit down on the rock to let this thought settle into something meaningful. You stare at outer space. No meaningful idea comes to mind. You keep trying and, tenacity eventually paying off, an extraordinarily beautiful picture suddenly emerges in your mind. You start to see curves and slopes and hills everywhere, around rocks and faraway planets and stars and galaxies. Light rays coming from bright faraway sources seem to slide around these slopes, leaving evanescent fluorescent lines on their paths, for you to picture them, for you to see the real shape of the universe's canvas. You see that, just like matter, just like you, light in space does not travel along straight lines, as you might have thought. Near a galaxy, a star, a planet, or even a little rock, light gets deflected. The denser an object and the closer a ray swooshes by it, the more pronounced the deflection. As the planets and stars and galaxies move, so too do the curves and slopes that they create, following them as they dance around one another and merge. Everything moves, everywhere, in this universe of ours. Even its fabric. It seems to you that this very fabric whose shape you are seeing, this fabric which has remained invisible to you up to now, in fact looks almost alive. Watching all this as you sit on your asteroid, you are sliding down a curve, just as you are right now as you read this book. On the asteroid, it is the rock that creates it. While reading this book, it is Earth. On the asteroid, the curve is gentle and it would not require much energy for you to fly away from it. On Earth, the curve is steeper. If you do not have the impression that you are falling as you read this book, it is because there is ground under your feet, or a chair you are sitting on, that prevents you from doing so. But you probably do feel that your shoulders tend to be dragged down. All the time. However, if you are reading this while free-falling from a plane, then you'd really be falling down the curve created by the Earth, although the presence of air would slow down your fall. Such a fall down a slope in the fabric of the universe is the most natural motion of all, for and around all objects throughout the universe. When you first pushed your ugly vase away, it slowly climbed the invisible slope your presence created, and then it fell down that very same slope, just like an object thrown upwards from the surface of Earth slows down as it moves up, and then speeds up as it falls down. To make it to space from the surface of Earth, an object has to be thrown vertically at more than 40,320 kilometers per hour. Shoot it slower and it will fall back down. 19 always. To escape your gravitational attraction, a minimum velocity is also required, just as a minimum initial speed is required if one wants to roll a child's marble up and over a bump in the ground. You did not push your vase fast enough, so it came back to you, because you, too, curve the fabric of the universe. And later, when you whizzed around the planet and swung out the other side with a little extra kick taken from the planet's own movement, you unknowingly used a technique that space rocket scientists use to send satellites far away in the solar system without needing any fuel, by having their apparatus fly near to planets at the right angle and distance. They can get them slingshot towards deeper regions of our cosmic neighborhood, with boosted velocity. As these thoughts wash over your brain, you now understand that even on Earth, everything is indeed falling all the time down the slope created by the matter our planet is made of. That is how and why our planet is layered, from the top of its sky to its innermost core, with the least dense particles above and the densest ones buried deep inside. It took billions of years for such an equilibrium to be reached. Now, whether you are aware of it or not, you just got rid completely of the idea of gravity being a force. Rather, you now see it as a landscape of curves and hills and slopes, and it seems that this was the lesson you just traveled to space to learn, for as soon as you think this, you suddenly find yourself back in your villa, lying down on your bed, facing your great-aunt who seems rather confused. Did I not just give you a vase? She wonders, seeing none in your hands. What vase? Never mind, dear, never mind. But what are you doing here, you ask? Your friends called me. You've been having hallucinations, they said. About gravity. When you're my age, you'll find its force to be a real drag. But you're young and shouldn't worry too much about it. Now, look at these vases I've brought you. Aren't they lovely? There's no such thing as a gravitational force, just slopes, you tell her rather moodily, silently cursing those treacherous friends of yours. Slopes, yes, I know, she replies unexpectedly while unpacking all the vases. And to your great surprise, she even counters that, gravitationally speaking, force or slope or whatever has never made any difference to her. Doesn't one usually shout help? I'm falling, rather than help. I'm being pulled down. How silly of you to make such a fuss about it. And then she goes on to redecorate your until now tasteful holiday villa with the dozen vases she brought with her, and you look at her, silently pondering what life is all about. That night, as you eventually manage to find some time to be alone, you escape the relative civilization of your villa to stroll the beach and face the stars. Your great-auntie's comment about gravity niggles you, and you try to summarize what you've just learnt. There are slopes in the very fabric of the universe. Everything creates a slope in every direction, an invisible slope that we call gravity, and the denser the object that creates it, the steeper the slope. But if all massive objects bend the fabric of our universe, then surely light also does, you think, because energy is mass and mass is energy, as per E equals mc. But is that really true? Does everything really bend that fabric, light included? And what the dickens could that fabric be made of? Back there, in your villa, or anywhere you've ever been, have you ever felt it? Have you ever felt the invisible slope created by a wall? By a sofa? By a ceiling? Or by the sky? Or by the light coming from a lamp? No, you have not. You've only ever felt the one created by our planet as a whole, the one that your muscles and bones fight in order to get up in the morning. Were you made of pure water, you'd splash and spread on the floor, not on the wall. In truth, whatever gravity you are feeling right now is actually the sum of all the slopes created by everything that surrounds you, including the walls and the ceiling and even a bird or a plane that might fly high above your head. But everything that is below you right now is far more significant than anything that is above. The earth beneath your feet contains more matter and stored energy than the sky above your head. So it creates the steeper slope. Hence you are inclined to slide down that one first, and feel it most. That's Earth's gravity. But what about the fabric of the universe? What is that fabric? What is bent? Well, that is actually what Einstein figured out. With E equals mc, he showed that the distinction between mass and energy is superfluous, that mass and energy are but two aspects of the same thing. That was in 1905. In 1915 he showed that the shape of the universe in any given place is determined by the mass and energy that is present in that place. In passing, he got rid of the idea of gravity being a force. Gravity is just geometry. Curves and slopes. Created by matter and energy. But the geometry of what? There's no such thing as a cosmic stretching soapy rubber cloth upon which everything moves, that is clear, but remember, just because we do not see something, doesn't mean that it does not exist. Before mankind understood that the invisible air around us is made of atoms and molecules, everyone thought it was empty. We here have the same kind of conceptual gap to bridge. Outer space, despite its seeming emptiness, is not empty. Nor is it static. What makes it a moving and changing geometrical object is precisely what I have until now called the fabric of the universe. Einstein discovered that this fabric is a mixture of space and time, two entities that, as we have learned to accept during the past century, can't be separated. The fabric of the universe is thus now better known under the name spacetime, and Einstein's general theory of relativity tells us how this spacetime is bent by what it contains, and vice versa. Energy and matter on the one hand, and the geometry of spacetime on the other, are identical concepts as far as gravity is concerned. So far, however, you've only experienced the bending of space. Not of time. Or so you think. In fact, the bending of time was always occurring. It even takes place around you right now, as you read. Its effects are too weak to be noticed by your senses, but you will soon find yourself in places where the bending of time will be obvious, and very confusing. This will happen in an aeroplane, in part 3, and when you eventually dive into a black hole, in part 6. For now, however, you are back on your beach and watching the stars. It is late, but you do not care. You stare at the heavens and you certainly feel like you are floating in the middle of wonderful ideas that seem completely crazy, but which, for some pretty miraculous reason, seem to be very good at describing our cosmic reality. Thanks to our planet's bending of space-time, everything that is close enough to it falls down towards its surface and adds to the bending. Thanks to this, over the billions of years since Earth was born out of a cloud of stardust, an equilibrium has been reached where our planet got surrounded by an atmosphere, the one that now protects us from outer space, allows us to live by breathing air and gives us the opportunity, sometimes, to stare at the sky. Just outside this atmosphere, away from Earth, there is our moon, which spins around our planet like a marble spins in a salad bowl, with this difference, that the moon itself also creates a bending in spacetime. The moon's own bending of space-time makes the water that lies here on the surface of Earth fall moonward. That is why the water follows the moon as it orbits our world, creating the tides. Point 20. Further away still, there is the sun, with the steep bend of its space-time slope, down which all planets and comets and asteroids of the solar system are spinning and whizzing at different velocities and heights, like marbles on the wall of that salad bowl. And then there is competition with our neighboring stars. Some distance away, other stars' bending of spacetime becomes more pronounced than that of our sun, and those faraway comets that lie near the limit may sometimes reach the tip of the hill and move from the realm of one star to that of another, just as a marble thrown from the top of one salad bowl might fall down into another, if there is one nearby. In space, there is always one nearby. And all the space-time bending of all the stars in the Milky Way adds up to create our galaxy's bending, our galaxy's gravitational field, which competes with that of neighboring galaxies, and then the local group itself competes with the aggregate bending of other groups, and so on. And Einstein figured out a way to understand this all in one single formula. Well done, Einstein. You almost wish he could appear right now in front of you, so that you could shake his hand, but you have the feeling that there is still more to figure out. Something even deeper. But what? Did you not read, earlier, that Einstein opened the door to the idea that our universe might have a history? That our universe was smaller in the past? You sit down on the beach and close your eyes, focused, ready to picture exactly what that might mean. 7. Cosmology. There are some questions in life for which a single and uncontroversial answer can be given. Unfortunately, despite what you've just seen, what our universe looks like as a whole is not one of them. Einstein's equations allow for many different global shapes for our universe, and, as you will see in part 6, we do not even really know what our universe is made of. Having said that, it may be noteworthy to remind ourselves that physics, however powerful it has been up to now, has never exactly matched reality. It even knows it can't aim to, because it would mean that reality, whatever it is, could also be exactly known. Which it can't. Observations and experimentations, whatever their accuracy, always give an approximate answer. There is always an error margin, however small that margin may be. With hindsight, we even know that throughout human history, the technology with which we humans have probed nature has only rarely been in step with what physics could predict at the time, sometimes leading to wrong beliefs. If, a few hundred years ago, an ancestor of yours had somehow managed to guess the existence of some bacteria whose size are 1,000th the width of a hair, none of his contemporaries would have been able to check this out, and he probably would have ended in an asylum for unduly scaring people. The same goes for faraway galaxies. Had your ancestor also insisted upon their existence, he would not have been locked away but burnt alive. Like Giordano Bruno. The necessary technology to see far enough into the cosmos to picture them did not exist until less than a century ago. Likewise, the technology to check what you will see at the end of this book has not been engineered yet. That being said, science progresses by steps, and sometimes by huge steps, opening the path for revolutions in understanding. Still, it may be healthy to look at science as being like scaffolding for thoughts, scaffolding that tries, generation after generation, to be as close as possible to the reality we live in, a reality whose mysteries are then unraveled through experiments. And it could well be worth mentioning that even though it may change in the future, so far no human activity but science has ever led to discoveries about nature that weren't there to be seen in the first place. However humble one needs to be before the majesty of nature, science, and only science, has given us eyes to see where our bodies are blind. So what does Einstein's vision give us that we didn't have before? If his equations are too hard to solve, what are they good for? If we don't even know what our universe is made of, how can we use them? Well, contrary to what most people may believe, scientists don't like complexity. They prefer everything to be simple. And the game, usually, is to figure out a simple pattern within a seemingly complex environment. That's where some wit comes into play. So, let's see what we can make out of Einstein's vision by simplifying, on as large a scale as possible, everything you've seen so far. Let's forget about details. Let's have a look at the big picture. No asteroids, no planets, no stars. They are far too small to be important for what matters here. Let only galaxies, clusters of galaxies even, remain. And you are there, able to see it all, as a long-sighted eye of such cosmic proportion that the Earth, the Sun, and the hundreds of billions of stars that make up the Milky Way are but a dot marking your position. The other galaxies are evenly spread around you, even though structures that resemble filaments are apparent. Good. That is simple. This is your initial setup. You feed it into Einstein's equations to see what, if anything, comes out of them. And you wait, anxious, not daring to expect much. And then... a miracle! It works! All around you, everywhere you look, the galaxies and clusters of galaxies move around each other as expected, but that is not all. The universe that surrounds you, the volume of the visible universe that can be observed from Earth, starts to expand. Spacetime stretches in between all the galactic dots, making them move away from each other, independently of how they move around each other. Whatever their movement on a small, local scale, they are like poppy seeds in a cake being baked or dots on the surface of an inflating balloon. The further they started from Earth, the faster they move away. That is what your friends saw when you gave them their billion-pound telescope. That's the expansion of our universe. By feeding Einstein's equation with a simple model of the visible universe, you got something that, before Einstein's time, had never been imagined at any time in the history of mankind. Something that corresponds to what you saw up there in the sky, to what scientists see every day. The universe itself can and does evolve. With such a thought, cosmology, the science of figuring out the past and future history of our universe, was born. Before Einstein, we only had cosmogonies, stories we told ourselves in order not to go mad about the mysterious origin of our reality. Now we have science too. A means to unravel the story that not humans, but nature, has written. As you watch all the dots that surround you evolve, you suddenly realize that, with Einstein's equation, you can indeed press rewind in your mind to make the expansion roll backwards. And you do. Instead of inflating, the poppy seed cake that is our visible universe immediately starts to deflate. Your cosmic eye sees it shrink. The pasts that were far away now move towards the present, towards you, swallowing away the images of the years to come. It is the whole sphere limiting Earth's visible universe that shrinks. And shrinks. And shrinks, until... About 100 years ago, when Belgian physicist and Jesuit priest Georges Lemaitre decided to implement the three cosmological principles into a similar, imaginary clockwork universe in order to watch it expand and contract in time, his conclusion was straightforward: our reality, it seemed. The very reality that had been taken for granted since humans were able to think, probably had a beginning. Einstein's equations had quickly led Lemaitre, and many others afterwards, to the very confusing idea that our universe, even though it has always contained all the energy it still has today, once had no size at all. No size in space or in time. An idea that definitely sounded absurd, and arguably still does, but that was what Einstein's equation said. From what we know today, however, this seems to be the best idea humankind has ever come up with to understand what we see in the night sky. Any theory that asserts that everything our visible universe contains once had zero size at some stage in its past is called a Big Bang theory. Hot because only a very hot past can cope with having all the energy of our visible universe squeezed into a very tiny volume. The heart of the sun is hot because all the matter it contains is squashed by the sun's own gravity. Shrink the whole visible universe into a sun-sized sphere and you get another level of hot. Big because it involves the entire visible universe. And bang because the expansion that followed makes it look like there was an explosion in our past, right after our universe was born, although you will see later that it wasn't an explosion at all. An extraordinarily, tremendously, mind-bogglingly, beyond blisteringly scorching, hot, huge, ubiquitous, universal deflagration may convey the idea of what happened back then better, but hot Big Bang is quite efficient too, and more humble. And humble it should be, for even though it may seem to your cosmic eye that everything about this Big Bang is centered on our planet, Earth, it is not the case. As you will now see, the Big Bang did not happen at one particular point in space-time, but everywhere. 8. Beyond our cosmic horizon. When you were on the beach, at the very beginning of your journey, you wondered whether what you could see in the sky, with your naked eye, was the entire universe. You now know it is not. Our eyes only allow us to spot a few hundred stars, all belonging to our galaxy, the Milky Way, and some faint traces, for those who know where to look, of a few other close-by galaxies. Using telescopes and other powerful tools, the whole observable universe, you now know, is unfathomably bigger than that. But it too has a limit, the surface of last scattering. This surface lies in our past, some 13.8 billion years ago. But it also lies in space, about 13.8 billion light-years away. 21 It limits what we can see today. Any light coming from further away would have had to travel for more than 13.8 billion years to reach us. But more than 13.8 billion years ago, light was not allowed to travel freely. It was stuck. The whole universe was too dense back then. Light only became free to shoot through space and time 13.8 billion years ago, and the last scattering surface is the image that remains of that moment. Seen from there, it marks the beginning of a transparent spacetime. Seen from Earth, it marks the edge of the visible universe. In a sense, this surface is our cosmic horizon. We cannot see further. Not from Earth anyway. Since the beginning of this book, you've been traveling within the universe as it is seen from Earth. You've always limited yourself to the visible universe, the universe that lies within our cosmic horizon, a horizon that is centered on us. But what about the universe as it is seen from somewhere else, from somewhere that is not Earth? Would the cosmic horizon there still be centered on Earth? Picture yourself drifting on a raft, in the middle of the ocean, far away from all lands. The horizon is clearly visible to you, a line separating the water and the sky. Looking around, you can see that it forms a circle whose center is you. Does that mean you are at the center of the ocean? Of course not. It means you are at the center of the part of the ocean you can see, your visible ocean. There is no way you could see beyond its edge, beyond this horizon of yours. But it doesn't mean that there is no such beyond. There is. Of course there is. A friend drifting on another raft some distance away would also have a horizon surrounding her. Her horizon, delimiting her visible ocean. If she is close enough, she could be within your visible reach. Your visible oceans would then have some waves in common, but she'd be able, in some directions, to see further than you, further than your horizon, and so would you of hers, in the opposite direction. But she could also be beyond your horizon in the first place. In that case, you could well have parts of your visible oceans in common without knowing of each other's drifting existence. A third possibility is that your friend is so far away to start with that her visible ocean and yours have nothing in common at all. As seen from the sky, it'd mean that the circles limiting what you can each see do not intersect. Whatever could be seen from where she is would be entirely hidden from you. She could be watching some volcanic islands and whales, but you would know nothing of it. In space, it is the same. The visible universe that we can see from Earth is a sphere 13.8 billion light-years in radius. But that doesn't mean there is no beyond. Someone else, on another planet, would be surrounded by his or her own cosmic horizon, which also would be 13.8 billion light-years in radius, because there is no reason for the universe to be younger or older there compared to here. The three cosmological principles you've heard of before have been introduced to ensure this. A visible universe so remote that it has no visible part in common with our own should look similar to ours, and obey the same physical laws. Even if her raft were too far away for you to see her, you wouldn't expect your friend's visible ocean to involve flying mountains. The same goes for outer space. The laws of nature should be the same everywhere. and no particular location should differ in this respect from any other. It follows that the visible universe seen by anyone living anywhere in our entire universe should also be expanding and obey Einstein's equation, meaning that if we were to rewind time we would find a Big Bang, just like here. A Big Bang centered on them, this time, not on us. With such a vision of our whole universe, there is no such thing as a center of it all, and the Big Bang occurred everywhere. With such a vision, you get a taste of what one calls a multiverse, a universe made of many separate ones, unable to communicate with one another, although they all belong to the same whole. You will see 4 different instances of such multiverses before the end of this book. This is only the first, and I introduce it first because most scientists do believe it to be correct. Now, accepting this, does it mean that the whole universe, that everything one gets by patching together all the visible universes as seen from everywhere, is infinite? No, it doesn't. The whole ocean, for instance, the ocean one gets by patching together all the visible ones seen from however many rafts you like, is finite. The whole universe is finite, then? No. It may well still be infinite. We don't know. As I mentioned at the beginning of the previous chapter, Einstein's equations unfortunately do not give us an answer to that question. All right. Now, what has been proven here? Not much, you think? Nothing, even? Perhaps even the Big Bang theory seems weak to you, just an abstract thought. Well, it is true that one could argue that what your friends saw in the sky merely indicates that the universe is currently growing. Many possible paths could have led to such an expansion. No need to introduce all this Big Bang nonsense. One could argue this, yes. But not for long. Science is not politics. Nature does not care much about anyone's opinion, even if they are in the majority. Hard experimental proofs are always necessary. And as we will now see, there are indeed some hard pieces of evidence for a Big Bang lying in our past, hints that are so compelling that some people go as far as to consider them proofs. 9. The Big Bang smoking gun. Were our universe to have been smaller in the past, how could you prove it? Physically time traveling there is not an option, but you could look into the past. By now, you should be used to the fact that when you gather the light coming from stars shining billions of light years away, you are seeing what they looked like many billions of years ago. You are watching the past. You can therefore check if the universe was smaller back then, or look for hints to this effect in the way light reaches you. It is not always easy, however, to make sense of what one is seeing in the outer reaches of the universe. By far the best way to proceed is to have a firm picture of what to expect and then check whether that picture corresponds to reality. That is what theoretical physicists do. But for now let us see what conclusion you can reach before looking up through a telescope. You are back on your tropical island beach. It is deep into the night, but, instead of watching the stars, and after checking twice that no one is around, you start talking to yourself, thinking out loud, to build a picture of the history of the universe in your mind. If the universe is expanding, then it must have been smaller in the past. Okay. But if it was smaller in the past, then gravity, or the curvature of space-time, must have been much more pronounced back then, since all its matter and energy must have been contained within a smaller volume. That is what Einstein's equations say, anyway. All right. Back then, space-time grew because, for some reason, there was an expansion. It started out tiny and very densely filled with matter and energy, and then, after 13.8 billion years of expansion, it became what it is now, with planets like Earth and stars like those you can see above your island. If that is the correct picture, back when the universe was small, whether it was dense with mass or with energy actually doesn't make any difference, since mass and energy have the same effect on the geometry of spacetime. That's what Einstein also said. So far, so good. Now, if all that energy was contained in a tiny volume, then there surely must have been a lot of friction and other things happening, and it all must have been very hot in the early universe. Sounds fair? Yes, this is not the first time you've reached that conclusion. But then, there are other conclusions one can reach from this. Like this one, the universe could have been so dense that none of the light around at the time could have traveled through it. No light could have traveled through it. That sounds like a wall. It does, you are right. Well done. Such a place must have existed at some stage in our universe's past if the expansion model is correct all the way through, and, well, such a place does exist. You've seen its surface. It is the surface of last scattering, the surface that limits what can be seen of our universe. What you've just done is quite extraordinary. You've just lived a physicist's dream, from pure logic, using Einstein's equations and what you've seen of the universe since you left your beach. You figured out that a wall opaque to light should exist out there in our past. That its surface should still be visible, and it is. This surface has been detected experimentally and somehow mapped, as you will now see. I understand that, while reading this, you may not feel like you've just revolutionized our vision of the universe, but that is because you have been introduced to that wall before thinking about it. You didn't spend 20 or so years of your life trying to prove that it should exist, long before it was seen. Those who did, however, felt incredible when the wall was proven to exist. How was it proven? Well, as you now start strolling the beach again, you realize that there is a problem. The surface that you saw at the edge of today's visible universe did not quite match the one you just thought of, did it? The real one, the one we can see through our telescopes, is very cold, whereas the wall you just pictured in your mind is supposed to have been very hot. How hot? Using Einstein's equation, some people actually did calculate its supposed temperature. And they came up with a rather large number, around 3,000 degrees Celsius. The whole universe, when it became transparent, must have been that hot, they discovered. The wall you saw in the sky wasn't. And that's a problem. But haven't you forgotten something? Didn't you suppose, to infer the very existence of a hot past, that space-time expands, that the universe's visible volume has been growing up with time, to match what your friends saw in the sky? And could that expansion have an impact on the universe's temperature? Well, yes. Not only could it, but it should, and that actually changes everything. Take the oven you have in your kitchen. Heat it up so that the air within it is lovely and hot. Then switch it off and imagine that the oven undergoes a rapid growth to become the size of a building. The temperature inside will instantly be much lower than it was when it was tiny. Calculations made as early as 1948 by U.S. scientists George Gamow, Ralph Alpher, and Robert Herman showed that, due to the universe's expansion, only a faint trace of the above-mentioned 3,000 degrees Celsius radiation should remain and fill our entire visible universe as if emanating from the surface of your wall. What temperature did they expect to find? Something around 260 degrees COR, 270 degrees C. Something between 3 degrees Celsius and 13 degrees Celsius above absolute zero. And it so happened that in 1965, some 17 years after Gamow and his colleagues' guess, two U.S. physicists called Arno Penzias and Robert Wilson found a peculiar job for the Bell Laboratories in the U.S. They had to set up an antenna to receive radio waves echoing off a balloon satellite. A nice easy job, were it not for a rather strange hindrance, a troublesome noise they heard throughout their signals. To get rid of it, and get paid, they did some brilliant checks and looked for many potential engineering faults. But nothing worked. Whatever they did, the noise remained unchecked. Eventually, finding no other reason for it, they blamed pigeons, or whatever birds were flying by, for having relieved themselves on their state-of-the-art antenna. Despite their impressive academic achievements, they went on to spend a long time furiously cleaning their device, cursing the existence of birds. But the noise failed to disappear, and they ended up calling some theoretical physicist friends. Soon after, they realized that they could have tried to get rid of that noise forever without the slightest chance of succeeding. What they were hearing was not due to some bird's gifts. The noise was not even from Earth. It was a signal. A signal with a temperature of 270.42 degrees C. And it was coming from space. From everywhere. Gamow, Alpher, and Hermann had predicted it. It was a consequence of Einstein's equations. It was the leftover temperature of the last opaque moment of our universe, a freeze-frame snapshot of a moment over 13.8 billion years ago, when a much smaller universe was so densely filled with matter and energy that no light could yet travel through it. 22. Penzias and Wilson had experimentally confirmed a prediction of a theory that seemed so absurd to some scientists that even its name, the Big Bang Theory, was coined by one of the most renowned professors of the time, British scientist Fred Hoyle, from Cambridge University, just to ridicule it. Penzias and Wilson received the Nobel Prize in Physics in 1978. They had discovered the heat that remains from the furnace our universe was a long time ago, the heat that radiates from the surface of last scattering, the surface that marks the end of the visible universe. 23. This radiation, one of the Big Bang smoking guns, is called the cosmic microwave background. Penzias and Wilson had proved that the Big Bang theories were on the right path. Now, why is this radiation called microwave? That, again, is related to the expansion of the universe. Light emitted at the time of the last scattering, when the universe became transparent, was very visible indeed and contained different colors and energies and frequencies. But it is no longer visible to our eyes, it got stretched. Do you remember that the color and energy of light waves depends on the distance between two successive crests? Well, stretched by the expansion of space-time for 13.8 billion years, starting with the color indigo, it gradually turns blue, then green, then yellow, then orange, then red, then it becomes invisible to our eyes, and turns infrared, and then exists only as radio waves and eventually microwaves. We are at that stage today. What once was visible as hot, visible light has now become, after 13.8 billion years of expansion, 270.42 degree cold microwave light. With this realization, Big Bang theories were suddenly nothing to joke about anymore. But what do these theories mean? Do they suggest that the universe was created at the surface of last scattering? No, they don't. You've seen, in the last chapter, that the surface we, on Earth, see at the end of our visible universe means nothing for observers who are not on Earth, they have their own. But now what about us? If the universe wasn't created there, there must be something beyond. What might we find there? Do we know? Is that the Big Bang? Well, in a way, yes. The Big Bang lies behind the surface. But not right behind. It happened 380,000 years before. 380,000 years before the universe became transparent. Behind the surface of last scattering, what later became our visible universe can be described as a soup of matter and light and energy and curvature that gets denser and hotter. You will soon be ready to travel there and see it all for yourself. But for now, let's just say that the further you travel beyond the wall, into the deep past of our universe, the more extreme everything gets. Traveling too far beyond, you end up surrounded by nothing that makes sense anymore. Even space and time end up being so curled up that Einstein's equations break down and can't keep track of what is happening. When this happens, theoretical physicists reach a place where nothing can be said about anything anymore. This moment can be considered to be the birth of space and time as we know them. According to the definition we shall use throughout this book, it is beyond the Big Bang itself. To reach this place and figure out what the Big Bang is will be your mission in Part 5. In Part 7, for your final journey, you will go even further, beyond the very origins of space and time. Why not go there right now? Well, because for now you should take a few seconds to breathe and congratulate yourself. You've come a long way since you first landed on the moon. You've learned many facts about the universe that your great-grandparents would never even have imagined possible. You've learned that our universe's fabric is a mixture of space and time called space-time, and that not only is it shaped by what it contains, it also evolves according to its geometry and contents. You've learned that it is huge by any standards, even bigger than we can see, and that we do not know its shape or its extent. Our visible reality is large indeed, but it has not always been so. You've learned that the universe has a history, that it most probably had a beginning, about 13.8 billion years in the past, hidden behind a surface opaque to light. And you've learned that it has expanded ever since, growing bigger by the minute. And you should be proud of having figured all this out. Why not go straight to our universe's beginning, then? A good reason could be that you should try to figure out what our universe contains first. Without that knowledge, you stand no chance of ever unraveling its deepest secrets. Neither about its possible origin, nor about its possible fate. All right, let's do it, you shout to yourself, opening your eyes. A gentle night breeze blows over the ocean. The moon is full. Its round surface reflects rays from the sun, bathing your island in silver light and shadows. A few turtles shyly crawl out of the water to spend the night on the sand, and maybe to lay their eggs, if the day is right. And you feel incredible. I'll be back, you shout at the stars. But you are not alone anymore. As you become aware of whispers behind you, you turn around, only to see your friends debating your situation with your great-aunt. Having heard you talk to yourself on the beach all night, they decided to move your departure date forward and looked for the earliest flight home. Your plane takes off in a couple of hours. You should pack and get some rest, they say. And your shouts and complaints and philosophical objections and speeches about freedom make no difference. You are being sent home. Now, however sad you may be about leaving the sea and the birds and the sweet wind, let me just tell you this, your journey through modern scientific knowledge has only just begun. Part 3 Fast. 1. Getting ready. Our senses are adapted to our scale, to our size, to our survival here on Earth. Our eyes are tuned to judge whether a fruit is ripe enough to eat, our ears to listen for danger, and our skin to the cold of ice and the heat of fire. Our senses allow us to see, to smell, to touch, to taste, and to hear our environment, this world, this reality within which we live. But this reality is not the whole picture. We are rather small compared to our planet. And the Earth itself, in turn, isn't much compared to the cosmos, as you have seen in your travels through the universe. It would therefore be rather strange, would it not, if, in order for us to survive on our modest little planet, our bodies had instead evolved spectacularly high-spec senses, able to register every known and unknown stimulus in the entire cosmos. In the everyday life of a human on Earth, for the whole of human history thus far, our bodies simply have not needed to apprehend the mysteries of the subatomic world, the speed of light, and the full array of light, from microwaves to X-rays. Indeed, we cannot even tell the difference between two extremely hot temperatures, or for that matter two extremely cold ones. They would melt or freeze our fingers before we could judge their subtleties. It is much more important, for our survival, to pull our hand out of the fire, or to protect it from the cold. We can detect the mild acid of a lemon with our tongue, judging whether it is good to eat, but we cannot judge the caustic difference between sulfuric and hydrochloric acid. They would burn a hole through our tongue. Similarly, our bodies do not feel the curves of space-time beyond their straightforward gravitational effect. As far as our everyday lives are concerned, all we need to know is that we are safely on the surface of our world. The world we perceive through our senses, then, is by its very nature limited. Our senses are our windows on the world, but they are only tiny portholes looking out on an immense sea of darkness. And for millions of years, our intuition about what we confidently call our reality has had nothing but these sense perceptions to build itself upon. But that is not the case anymore. We can now see beyond our senses. And beyond, reality changes. In the first 2 parts of this book, you've traveled far and wide. You've crossed intergalactic voids and even glimpsed just how big this universe of ours is. You've discovered that what Newton thought was universal about gravity actually isn't. Gravity, as Einstein told us, is the result of a bending of spacetime. It is not a force. Newton taught us how to use words and equations to describe and forecast the behavior of the world we detect through our senses. Einstein, with his theory of general relativity, carried you beyond, and it was not your animal senses that allowed you to follow him there. It was your brain. Using it, you discovered a law that merges space, time, matter, and energy into a theory of gravity. This was your first beyond. You are now about to enter 2 different beyonds, like an adventurer strolling newfound continents where nothing is familiar and where nothing can be taken for granted, not even the laws of nature. The first of these 2 beyonds is the realm of the very fast, and the second, the richest of them all, that of the very small. They will definitely look rather alien to you at first, and I guarantee that your common sense will be screaming at you that what you encounter simply feels wrong, but remember, all the matter your body is made of belongs to these exotic lands. The fact is that you are built out of realities for which the rules of nature are very different from the ones we are used to experiencing while lying on a sun lounger on a tropical beach. Only by a very strange mechanism does the reality we perceive day after day appear to us as it does. 2. A peculiar dream. You are sitting in seat 13A, next to a window. There are 73 passengers on the airplane. They all look normal except for your neighbor. He looks weird. You try not to look at him and almost wish you had not asked to be seated away from your great auntie. You've only been on board for a couple of minutes, but you were the last passengers, and the plane is now ready to take off. Your holiday friends are waving you goodbye from the ground, visibly relieved to see you leave. You sigh, though. However eerie it felt, traveling through the universe was good fun. You're not that keen to be flying back home right now. The engines thrust the whole winged apparatus up into the sky, up the space-time slope our planet creates merely by being there. You are pushed against your seat and thus feel heavier than usual. You are actually experiencing gravity exactly as if you were seated not in a plane but on the surface of another planet, a planet whose gravity is stronger than Earth's. Yearning for another interstellar journey, you close your eyes and begin to fire up your imagination. A beautiful alien landscape appears in your mind, with strange trees and lakes in a sky with twin suns. You remember that in just the past few years, mankind has detected thousands of planets orbiting faraway stars, a handful of them potentially similar to Earth. The humming of your plane's engines slowly lulls you to sleep, and you start dreaming about being somewhere far away, flying in a futuristic plane through a pink, double-starred alien sky. A distant voice reaches your ears. It says that your plane has reached its cruising altitude and will now accelerate to the unprecedented velocity of 99.999999% of the speed of light. Some time later, as your plane starts its descent, a stewardess's voice wakes you up. A quick glance at your watch tells you that you've slept for 8 hours. You stretch and yawn, slide open the window lid and look out. There's only one sun. Its light rays are bouncing off morning clouds, giving them a pink hue not unlike the alien sky you were daydreaming about before falling asleep. Underneath the aeroplane, however, the surface of the Earth does not look as expected at all. A seemingly endless ocean spreads all the way to the horizon. You are supposed to be landing home in less than a minute, but all you can see is open water. Dark thoughts make your spine shiver. Has your plane been hijacked? The other passengers seem pretty relaxed, including your great-auntie a few rows ahead of you, and your strange neighbor is asleep. So no, not a hijacking. But still, something is wrong. Has the entire Earth become flooded while you slept? You've read somewhere that about 10,000 years ago the oceans all around the globe were much deeper than they are today, covering much of the continents. Looking out the window, you wonder, could you have traveled back in time to wake up above a flooded Earth inhabited by long-extinct species? The idea makes you smile, but you can't shake an uncomfortable feeling that something isn't quite right. You were asleep for about 8 hours, it seems. And traveling. Anything could have happened to you or to your plane while you were out cold. Throughout your life, you have probably, like everyone else, become used to waking up pretty much where you fell asleep. Now imagine you had never slept before, and you were to nod off for the first time in your life. You'd surely be pretty confused when waking up. The first thing you check would be where and when you are, as some of us still do in a panic when waking up away from home. In fact, away from home or not, most of us do systematically check the time when we open our eyes in the morning. Only on rather rare occasions after a particularly good party, for instance, do we also check the place. It so happens, however, that waking up in the same place in which you dozed off has never happened either to you or to anyone else. Ever. Earth does not stop moving when you sleep. Every hour that passes, Earth travels a little more than 800,000 kilometers around the center of our galaxy. And so do you. That's the equivalent of about 20 trips around the planet. Every hour. No one minds, though, as long as their bed stays still beneath their body. Were Earth, or just you, to also be traveling in time, however, it would be a different matter. But that is not possible. Time travel does not exist. Or does it? As you stare out of your plane window at a vast city in the middle of an ocean, you realize that you are not about to land on the Earth you left. Understandably, you start to panic and try to jump to your feet, but the seatbelt holds you down and the sound of the roaring engines covers your cries. You wave frantically at a flight attendant who frowns angrily and motions for you to be quiet before reaching for his microphone to remind everyone that any disruption during descent and landing is still, in the year 2415, punishable by law. You open your eyes wide. What year did he say? A second later, your plane lands on water and starts to cruise through an alley of glass skyscrapers whose style of architecture is alien to you. As you stare blankly out of the little window, you hear the stewardess speak again. With the smooth, professional tone used by flight crews the world over, she welcomes you home on June 4th of the year 2415, 4 centuries after your departure, 3 days ahead of the scheduled arrival. The time now is 25 past 10 a.m. and the morning mist is expected to clear soon, to give rise to some bright, sunny spells. All passengers should expect temperatures about 10 degrees above early 21st century averages. Thank you for choosing McFly Airlines, a member of the Future Skies Alliance. 2415. You glance at your smartphone. No signal. Typical. Fortunately, however, your watch still ticks. And it seems to be under the impression that you've only traveled for 8 hours. Not 400 years. Something is very, very wrong. Is this a trick? Did your friends plan all this? You check your flight ticket. It's a flight home all right. Have you been drugged? Worse still, could this be real? Is a debt collector going to be waiting for you at the airport to ask for 400 years of unpaid rent? And the person you recently arranged to go on a date with? And how about the milk you left in the fridge? Important practical questions race through your mind and make your head spin. 400 years in the future. And whose future, at that? Certainly not your own, since your body does not seem to have aged at all in the 8 hours since takeoff. The future of your friends and family, then? The city you've just landed in definitely looks like no city or town from the century you've grown up in. Time really does seem to have been fast-forwarded outside the plane while you were sleeping. But wait. How could time outside the plane have raced ahead on fast-forward while time inside did not? This sounds absurd. But it does seem to be the case. It actually is the case. And your aeroplane's exceptional speed is to blame. 3. A time of our own. Speed changes everything. Even space and time. A clock that is moving through space at a very fast speed does not tick at the same rate as a slow-moving watch gently attached to your wrist as you stroll on a tropical beach. The idea of a universal time, a godlike clock that could somehow sit outside our universe and measure, in one go, the movement of everything in it, how its evolution unfolds, how old it is and all that does not exist. What has just happened to you now, in your plane, illustrates this. The time we humans experience seems to be the same for us all, universal, but we experience it as such only because when compared to light, none of us is moving much more quickly or much more slowly than anyone else, which is very fortunate for watchmakers. But even though our senses may not be able to feel it, the fact remains that if all of the people, animals and objects that happen to be on our planet's surface were assigned their own clock, it would keep time differently to all the other clocks. We all have a time of our own, attached uniquely to ourselves. Einstein figured that out 10 years before publishing his theory of gravity, the general theory of relativity to which you were introduced in the previous part. Back then, unable to secure any kind of position in any university whatsoever because nobody wanted him, 20-something-year-old Einstein was making a living as a patent officer in Bern, Switzerland. But this didn't prevent him from thinking. In between evaluating patent applications, he tried to imagine how the world appears to moving objects, depending on their speed. He was looking for a theory of moving bodies. He wasn't yet obsessed by gravity, nor by the universe as a whole, just by how objects manage to move within it. At the age of just 26, in 1905, he published his work, and the whole scientific community soon realized that someone no one had ever heard of had made an extraordinary claim from a desk lost somewhere inside the Swiss intellectual property offices, that clocks did not always tick at the same rate. Rather, that the ticking of clocks depended on how they were moving relative to one another. Better still, the theory this unknown young man was putting forward could predict the actual time difference one should expect two travelers to experience, according to their relative speed. This theory is called the theory of special relativity. Let us imagine twins. Two of them, since they usually come in pairs. A couple of years after Einstein's publication, French physicist Paul Langevin calculated, using special relativity, that if one of the twins was sent in a rocket for a 6-month round trip away from Earth at 995% of the speed of light, the one who stayed on Earth would have to wait 50 years to see his sibling come back. So according to Einstein, 6 months lived by the one who left in the rocket ship should equate to 50 years for the one who stayed on Earth, and for the whole of humanity too, our planet would orbit the Sun 50 times during the traveling twins' voyage. Although they are twins, they would end up not having the same age at all, one being 49 years and 6 months older than the other. A rather astonishing claim. When you heat up a metal bar, it expands and becomes longer. It is said to dilate. If you aim the heat carefully, it is possible to have only the bar dilate, rather than, say, the anvil it sits on, that is, its surroundings are unaffected. According to Einstein's special relativity, a similar phenomenon happens with time. With a rocket shooting at 99.995% the speed of light or a plane flying at 99.9999999% of it, it is the rocket and the plane and everything they contain that move fast. not their surroundings. So it is their times, and their times only, that are affected by their extreme speed relative to the world around them. What Langevin's twins experienced, indeed what you have experienced flying in that extremely fast-moving plane of yours, is what scientists call time dilation. The faster one travels, the more pronounced the time dilation. A very peculiar phenomenon. But Einstein's special relativity also suggested something even harder to accept. It said that as your time undergoes a dilation, the very length of things should contract. Now, since you were fast asleep in your plane when this happened, please allow me to offer you another ride in the world of the very fast. You are about to see what our reality becomes when looked at while traveling at mind-bending velocities. So let's forget about your plane for now, and even about gravity. Picture yourself on Earth, in a spacesuit, and imagine you have a pair of rockets attached to your back, rockets that are so good that they never run out of fuel. You kiss your present life goodbye and get ready to shoot off. Spaceward. Now off you go, hoping that no random space rocks are in your path. You are not just a mind traveling through the history of our universe, but a mind and a body, as you were last time, embarking on a ride through empty space, just for the fun of it. You're already in space. You check your watch. It ticks the way it's always ticked. 1 second passes every second, it seems, whatever that means. The Earth is moving away behind you, but imagine that there is a huge clock hanging over it, a clock that you can always consult, wherever you are, showing the time ticking, say, in your great auntie's house, telling you what time and day and year it is there. Your thrusters are powerful. You are at 87% of the speed of light. 1 second still passes every second for the watch on your wrist and the cells in your body, but everything around you starts to become strangely distorted. You turn around to look at the clock above the Earth. As 1 second passes on your watch, 2 pass on your home planet. Uncanny. Your personal aging has halved compared to everybody still on Earth. But as far as your perception is concerned, a second always takes a second to pass. It is the Earth's clock that seems to be moving faster. You keep going. You are now moving at 98% of the speed of light. 5 hours on Earth now take one of yours to pass. You look ahead, at faraway galaxies. Strangely, all these shining blobs of light that seemed extremely remote a blink of an eye ago now don't seem to be that far away. It is as if galaxies out there had jumped closer. 5 times closer, to be precise. But that, surely, is not possible. You look at your watch and tachymeter. You are now flying at 99.995% of the speed of light, the speed Langevin gave to the rocket ship of one of his twins. It still isn't as fast as the plane you boarded, but even at 995% of the speed of light, clocks on Earth now tick 100 times faster than yours. A whole day and night on your home planet takes just 1 minute and 26 seconds for you. One of your years is a century back there in your great auntie's house. And those faraway galaxies ahead, those galaxies that are supposed to be millions of light years away, how come they suddenly seem so close? Surely they cannot be that close after only a couple of hours of traveling. Still, they are. 100 times closer. Their distance away from you has just shrunk by the same amount by which your time slowed down when compared to Earth's. This is not at all like the expansion of the universe, though. That expansion occurs in the same way whichever direction you look. Here, it is different. It only happens in the direction you are traveling. And it depends on you and you only. So forget about the universe. Just think about yourself and focus on what you see. To your right and left, nothing seems to have changed. Same for above and below, where distant galaxies are still pretty much where they were before you started speeding up. But the galaxies ahead of you definitely are not. Facing them again, there is little doubting that something fishy is happening. It is not just time that seems to be subjected to dilation, lengths and distances have also apparently become shortened, contracted. It certainly seems so. The whole universe looks to you as if you were peering at it through a distorted magnifying glass that shrinks the distances ahead, but not sideways. You check your watch. 1 second still ticks every second. And you are still accelerating, and everything seems to get even more distorted. Understandably, you become confused and scared, so you make a huge U-turn to get back to Earth, which you expect to be extremely far away. But it is right there. Turning your head around, the galaxies you were heading for a moment ago are now back where they were, extremely far away. Whatever the direction you are traveling to at this amazing speed, everything ahead, however far, seems to be but a stone's throw away, whereas the other directions don't change. A few minutes later, still confused, you shoot past the International Space Station, which moves around Earth at a completely insane rate. You check the ticking of your watch, still 1 second every second. You pass by an astronaut whose movements are accelerated 100,000 times. The hands of her wristwatch spin like mad. You see the difference between her time and yours. You see her life unfold. 10 hours pass on her watch as just one tiny fraction of a second passes on yours. And she moves accordingly. And so does the space station, and Earth, and everything around. And your rockets still fire their power, thrusting you past Earth. Faster and faster. Towards infinity, and half a second of your time passes and the astronaut is now back on Earth, and a couple of blinks later she's dead and her children have grown and had children, and the Earth spins thousands of days and nights and years, and you're too far away now to see anything of it anymore. A few seconds pass for you. You keep accelerating. No point in heading back to Earth now. You'd land in a future so remote that you'd probably feel like an antique, and surely would be treated as such. The whole universe ahead of you keeps looking closer and closer, and flatter and flatter. Sideways, still the same. Only ahead, in the direction you are traveling, do distortions occur. You are still accelerating. You are getting closer and closer to the speed of light, but something is not right again. Although your rockets have thus far been happily propelling you faster and faster throughout space and time, your speed has not been increasing much lately. Instead, it seems, your rocket's energy is turning into mass. Yes, you are sure of it. You are getting heavier by the minute. Years of diets ruined by rockets. Who would have thought? Wait, you shout, annoyed by this above anything else, and everything freezes. You are up there, floating somewhere far away in space, probably millions of years in our future now, but frozen still. Rather handily, so is the whole universe. Nothing is moving. You can relax for a moment. Good. Let's ponder together the 3 counterintuitive aspects of the high-speed trip you've just made. Firstly, time flowed differently for you compared to anyone on Earth, including the astronaut. The actual mechanical watches you were both wearing did not tick at the same rate at all, and the faster you flew, the more pronounced the difference. That is the first change. It is strange, I agree, but it is so. The second thing you experienced was that distances shrank ahead of you. What seemed very far when you were not moving fast became very close when you did. Which is also strange, I agree. But it is true nonetheless. It is called length contraction. And the third is that eventually you became more and more massive. Which is annoying to say the least, though perhaps not as unexpected as the other two, considering that you now know that E equals mc. So let's look at this particular byproduct of fast travel right away. Nothing with any mass can reach the speed of light, let alone break that speed. That's a law. So the faster anything with mass is traveling, the more difficult it gets to accelerate it. To see what this means in practice, picture yourself flying so fast that adding only 1 kilometer an hour to your tachymeter would mean reaching the speed of light. You then take a tennis ball out of your pocket and throw it ahead of you. Let's say for the sake of argument that you throw it at 20 kilometers per hour. On Earth, that'd be easy. But right now, it isn't. In fact, it is impossible. Nothing can move faster than light. So as you fly along at just 1 kilometer per hour short of light speed, your ball simply couldn't go 20 kilometers per hour faster. Nothing prevents you from throwing the ball, that's true, but if the ball can't travel faster than the speed of light, then clearly something else will have to give as you hurl it into the void ahead of you. And the answer is given by our old friend E equals mc. The extra energy you give the ball by throwing it forwards is turned into mass, since it cannot turn into speed. You already knew that mass could be turned into energy, and you here have an instance of the opposite phenomenon: energy is turned into mass. And that wraps it. You've just learned, thanks to Einstein's theory of special relativity, why you were becoming more and more massive before calling out and freezing everything. Now let's turn to the other two problems of your high-speed journey, the dilation of time and the contraction of lengths. Most people are both baffled and fascinated when confronted with the fact that there is no universal time. Our common sense, honed by millions of years of evolution on the surface of our tiny planet, intuitively rebels against the idea. But even though we can see its effects on us and around us, time is a rather abstract concept, an intangible flow of something that is entirely invisible. So despite its strangeness, we can surely cope with the idea of it not being as smooth as was once thought. Space, on the other hand, is something we believe we are familiar with. But that is a mistake. We are not. A meter is always a meter, you might think? Well, that is not correct. It depends on who is looking at it. Space and time are linked to one another. If time changes, distances also have to give. Why does it have to be that way, you wonder? Why do distances and lengths have to contract if time dilates? The answer lies in the existence of nature's absolute, unbreakable speed limit, the speed of light. Were distances not to contract, then you would already have violated this limit. In outer space, light travels at around 300,000 kilometers per second. An Earth-based observer watching you fly at 87% the speed of light would see you travel 260,000 kilometers in one of his seconds. Flying that fast, however, you must remember that the seconds you experience are now different from his. At 87% the speed of light, 1 second of yours equates to 2 seconds. On Earth and in those 2 seconds, the Earth-based observer sees you travel 520,000 kilometers. That's twice the distance he sees you cover in 1 second. Nothing peculiar here, right? Wrong. Because although you'd have traveled 520,000 kilometers in 2 of his seconds, only one of yours has passed. That's 520,000 kilometers per second, as far as you are concerned. The speed of light being 300,000 kilometers per second, you'd have smashed the universal record. But this is forbidden. Not by the police, but by nature. Remember, nothing can travel faster than light. At the beginning of the 20th century, many experiments had already established both that idea and the fact that in outer space, light always travels at that speed. Newton would never have been able to explain this with his vision of the world. But Einstein did. With his. In his theory of moving bodies, the special theory of relativity, times and distances have to dilate and contract in such a way that, whoever is watching, no object can ever cross the light speed limit from anyone's point of view. An Earth-based observer's time flows twice as fast as yours? Then the distances you travel are, from your point of view, half the ones the observer sees you cross. Flying at 87% the speed of light, you do not travel 520,000 kilometers every second, but 260,000. What seemed to be a kilometer for an Earth-based observer is actually half a kilometer for you. Your speed is always the same, whoever measures it, be it you or anyone else. Velocities are not observer-dependent. Only time and lengths are. If, flying faster, distant galaxies seemed much closer to you, it is because they became much closer. For real. And this does not just apply to distances, objects themselves shrink with speed too. As seen by anyone not moving along with it, any rocket and all its passengers would contract. Even you did. At 87% the speed of light, flying like Superman, fists stretched out ahead, you shrank to half your length as measured by someone on Earth. And someone flying with you would not have noticed it, for their tape measure would also have shrunk. And this is all a consequence of accepting a fixed, finite and unbeatable speed for light. All this is what Einstein wrapped up in his 1905 special theory of relativity, a theory that gives the rules of nature for anyone who cares to travel at high velocities. Strange? Yes. Counterintuitive? Definitely. But that's how nature works. Now, what about gravity? We purposefully forgot about it for a while. But if we are to have a realistic vision of our universe, we now need to bring it back. In a moment, you'll therefore continue your fast-moving journey through a universe whose fabric, space-time, interacts with its energetic contents and bends around them, creating gravity. Back to you. You are in outer space. Everything is still frozen. Earth is somewhere far behind you. The astronaut you saw has been dead and buried for a very long time. You were shooting straight for faraway galaxies that now seem much closer. Just remember that time and space are now inseparable parts of space-time, the fabric of our universe, and that gravity is the effect of the bending of that fabric by the energy it contains, whatever its form, and that mass is energy. You were getting more and more massive when you froze your journey. Let's unfreeze the picture. Ready? You are flying again. Your body is moving extraordinarily fast, and your thrusters are still powerfully hurling you forward. You are getting more and more massive, and so, since gravity is back in the picture, your increasing mass is curving space-time more and more around you. The mass of a small mountain is now contained within your body. Point 24. Rocks you fly by are beginning to slide down the slope you create, and soon they even begin to start falling upon you. They hurt when they hit you, but since you are getting more and more massive without growing in volume, you are denser than you were, so they shatter into tiny pieces. Collecting more and more energy, you become as massive as the Earth. You've captured big rocks and even small planets in your wake. They are orbiting you now. You are so heavy, the curves you create in space-time around your own body become so pronounced that the universe you see becomes distorted in every direction. Not just ahead. And this is not due to speed anymore, but to gravity, to the bending of space-time, to the energy that you have gathered within yourself. Because of this energy, space and time, intertwined as they are within the fabric of our universe, are so bent that wherever you look, the universe seems distorted and accelerated, as if your time was now slower than every other clock in the universe. You are about the mass of 5 Earths, all concentrated within your body. You are having a hard time lifting your hands, obviously, or anything else for that matter, and in fact now you can't move at all. To be honest with you, if I were you, I'd stop right here. Why? Because sooner or later, accumulating more and more energy within your own body, you will end up becoming a black hole. And that is not a good idea at all. Unfortunately, you are already too massive to move, so you can't even check whether some hidden switch can shut your rockets off. Your hands are now as good as glued to your hips, and you are indeed starting to collapse in on yourself and... Stop, you shout, in a panic, and you find yourself back in your plane, by your window. Your weird neighbor is looking at you. From his expression, it seems you woke him up. He is definitely weird, but right now, you probably look even weirder. You mumble an inaudible sorry and turn towards your plane window to stare outside. It is dawn. No sign of an immediate landing into a futuristic hometown. No sign of faraway galaxies being closer than they should be. No small planet orbiting you. You are simply flying. You stare at your watch. It seems you've been in the air for 8 hours. May I inquire why you cried out? Asks your weird neighbor. Where are we? What year is this? You ask in turn, eyes wide open. I beg your. What year? You insist, rather nervously. 2015, replies the man, somewhat amused. As the stewardess announces that the plane is about to begin its descent, you realize that you just dreamt it all, that you did not fly to the future, that you are still here, on your way to your lovely old normal hometown, with its concrete roads and brick-walled buildings. The outside temperature is 12 degrees Celsius, continues the stewardess, and the morning mist will begin to clear by midday. 2015, what a relief. But what a strange dream. For how to never get old. What you just experienced was not a pure flight of fancy, though. You really did get a glimpse of what the universe would look like if you could move very, very fast. Scientists have called velocities beyond which the strange effects you have experienced cannot be ignored any more relativistic speeds, and everything you've just dreamed obeyed the laws of nature, as they are understood today, from a relativistic perspective. No human has ever reached these speeds, of course, but the particles that surround us have. In fact, they do so all the time. But back in 1905, when Einstein came up with these amazing ideas, it was hard to check how they behaved. It actually took 66 years after the theory of special relativity was published for two American scientists, Joseph Haffel and Richard Keating, to devise an experiment able to detect the strange time dilation effects Einstein had forecast. We are in 1971. Haffel and Keating have acquired 3 atomic clocks, the best clocks ever made. Once synchronized with each other, they remain synchronized to an extraordinary level of precision. They don't change by more than a billionth of a second over millions of years. Very, very reliable clocks indeed. So, Haffel and Keating had 3 of them. Synchronized. And they took them to an airport. They kept one on the ground, in the airport lobby, and literally booked a seat for the other 2 on 2 commercial planes. Just imagining the reaction of the other passengers makes me smile. Anyway, both planes then took off. One flew eastward, the other westward, around Earth, before eventually landing back in their departure airport to join their Earthbound synchronized alter ego. Since Earth spins on itself in an eastward direction, flying eastward or westward does make a little difference to the overall relative speeds of the planes and airport. Now, were nature to behave the way our intuition believes it does, the 3 atomic clocks should remain synchronized whatever the planes do. A second is a second, to the universal clock that God keeps on his bedside table, so 1 second should tick every second. All the clocks you've ever seen or used, mechanical or not, certainly do agree on that. And that's it. Except. No, that's not it. Nature doesn't care much about what our intuition believes, and it so happens that this intuition is wrong. Our usual clocks are just not precise enough to tell us so. Our intuition may be wrong, Einstein's was not. Once their 2 planes had landed back at the airport, Haffel and Keating found that their 3 atomic clocks were not synchronized anymore. The eastward flying plane's clock was 59 billionths of a second late compared to the one that stayed in the airport. The westward one was 273 billionths of a second ahead. It would have taken more than 300 million years for such a mismatch to happen naturally, had the three clocks remained next to each other. According to Haffel and Keating, there were two reasons for this mismatch. The first is related to the speeds involved, to special relativity. As Einstein had guessed, the relative velocities of the three clocks should indeed lead to some tiny but measurable time dilation effects. The other reason, however, has nothing to do with velocities, but with gravity, with Einstein's general theory of relativity. Just as a heavy ball rolling on a rubber sheet bends the rubber more next to it than further away, Earth's effect on spacetime, Einstein said, should be more pronounced near its surface than far away in the sky, where planes fly, and will consequently affect the way time flows at different altitudes. These two effects, independent of one another, were calculated before Haffel and Keating did their experiment, and added up.